When the periodic signal has certain forms of symmetry, the Fourier series becomes simplified. We're going to look at three common simplifications that we run into, and one of these already came up, actually two of them already came up in the example we did a couple videos ago. The three types of symmetry are DC symmetry. This means that the area above and below the time axis are equal. So the DC component vanishes. The other type is even symmetry. And finally, we have odd symmetry. Even symmetry means that when I evaluate x at negative time, I get the same value at the positive time. So I can flip it about the vertical axis and I get the same function. The cosine is an example of a function that has even symmetry. The triangle wave that we did a couple days ago was aligned in time so that it had even symmetry. And we saw that when that happened, the sine components of the Fourier series disappeared. Finally, we have odd symmetry, which says when we look at the negative of a time and we compare that to the value of the function at the positive times, those will be negatives of each other. So the sine is an example of an odd symmetric function. So let's take a look at, for each of these three cases, how the Fourier series coefficients become simplified. So for a DC symmetric signal, which means the DC component is equal to 0, the A0 component will go to 0. So if you know you have this form of symmetry, you do not need to evaluate that integral. Since the component is 0, all three of these will be equal to 0. X of 0 also for the exponential form. And we did not specifically, explicitly cover the amplitude phase form, but the C0 there, which is the DC component in this form, also goes to 0. The amplitude phase form is taken by combining the cosine and the sine at a particular frequency. We know since the cosine and the sine are 90 degrees out of phase, we can find the amplitude as the hypotenuse of a right triangle, and we can find the phase shift as the inverse tangent shifted accordingly of the amplitude of the sine component over the cosine component. So the DC component here, C of 0, would be going to 0. Let's now look at the other two types of symmetry. First of all, let's take a look at even symmetry. When we have even symmetry, the sine components go to 0 because we have an even function times an odd function gives us an odd function being integrated over one entire period. So it's going to have equal positive and negative portions in order to be an odd function. Also, we can make a simplification to the a of n with the cosines. So remember, the integral 0 to t0 can be taken over any interval t0 wide, and we can also use it, for example, over the symmetric interval, which we often do from negative t0 halves to t0 halves. This one is convenient for seeing if I have a cosine and the cosine could be multiplied by any frequency, but I'm just doing cosine of x here as an example. If I have a cosine, I'm going to get, because of even symmetry, twice the area from 0 to t0 over 2 of the cosine at whatever frequency. Here I'm just showing it with x itself, and that will simplify my integration. Since the function is even, I don't need to evaluate both the plus and minus half period intervals, but I can often get some simpler calculation by finding the value at the value of the indefinite integral at 0 and subtracting that. So we can modify the formula here to say go over the half interval and then multiply by 4 instead of 2. The phase shift formula simplifies since the sine component is 0. We just have 0 when a of n is positive and 180 degrees or pi when a of n is negative. Also, in the exponential series, since the sine components, the b's, have completely disappeared, we end up with the exponential x of n have no imaginary components, so they are all real, in addition to the other types of symmetry that we had before. We have conjugate symmetry of the exponential if the signal is real. And if we additionally have the fact that we have even symmetry, we have x of n does equal x of negative n conjugate, but the coefficients are real numbers now. So x of n and x of minus n are negative, and they are real numbers. So here we say the x of n is equal to x of minus n, and those are real numbers. So that is what happens for even input signals. Finally, let us take a look at what happens for odd signals. Odd signals are where x of negative t equals negative x of t. When the signal is odd, the a of n for positive n will disappear because now we have x of t as the odd function, cosine is an even function, the product will still be an odd function, and the integral will vanish, as we've seen a few times now. So the a of n's go to 0 in this case. For the b of n, we have an odd function times an odd function. So we are still integrating an even function, which we must be. Otherwise, if we would be integrating an odd function, the area would disappear. So here we have x is odd, sine is odd, product is even. So the part for negative time has the same area as the part for positive time because we have a sign reversal in x as we go from negative to positive time, and we have a sign reversal in the sine function from negative to positive time. So we can use the same modification we used on the even signals. We get the integral from 0 to t0 over 2, so the half of the period, and we accumulate the area there, which is the same as the area from negative t0 over 2 to 0. So we multiply this by 4. Now, since the a components are 0, we are at the plus or negative 90 degree phase points on the phase function. So on the phase function here, we will get negative 90 degrees when b of n is a positive number, and we will get positive 90 degrees when b of n is a negative number. So those are some of the key simplifications that we make. Now, for our exponential Fourier series, the x of n are all going to be pure imaginary. And the exception, well, not exactly an exception, x of 0, the DC part has to be 0. Because that's one of the A's, and if the signal had a DC offset, that would make it be not even. So there is our simplification for the exponential series. So if we go back to the beginning of the class, we had any signal can be represented as an even signal plus an odd signal. When we do the Fourier series, we can say the Fourier series is going to be equal to the Fourier series of the even part plus the Fourier series of the odd part. The odd part will be pure imaginary, and the even part will be pure real. So if the signal is neither even nor odd, depending on how the signal is structured, we might want to break it down into even and odd components so we can use the shortcuts for the Fourier series of an even function and an odd function. In some cases, that's going to make the work easier. In others, it won't.